Yesterday's area, units squared. Today is volumes, units cubed. Okay, why would you want to learn some of this stuff? Well, we can model figures three-dimensionally, taking some functions and revolving them around an axis. Why would you want to do that? Well, maybe to save on production costs when you're designing some particular components for some mechanical device, drawing a better bottle that uses less material. Even though we can print 3D print things pretty conveniently now, you don't have to send stuff to China back and forth or whatever to get production done. You can have some models made pretty quickly. You still want to figure out some costs maybe involved in this stuff and get things planned out a little bit more. Like all those bottles over there, I guarantee they're modeled on some three-dimensional software. You're probably not doing the calculus all the time. There might be a couple people in the firm that maybe work with some of the calculus, but your computer is going to be doing most of it anyways. The important thing is to just know that how to do it or have some familiarity with it. So what is the disk method? Well, disk method is created by making disks. Disks are circles, right? Think about it as a frisbee, right? What we like to do, hi, come on, you guys can come in and stand anywhere. What we like to do is create some figure. And then we like to revolve it around an axis, which creates a two-dimensional figure. And then when we stack all those two-dimensional figures up, we create that three-dimensional figure. So when you take that area and you stack up a whole bunch of things that have area on top of each other, that means you have an area, then a width. Now you have volume. Okay. Before we had height, and then we stacked a whole bunch of those heights, like pencils up. Then we had width, we had area. Now we're going to take area, spin it, to create volume. Okay, this is called the disk method. Is because there is no hole in the middle. It's not a donut, it's not a washer. So this would be a disk, stacking a whole bunch of circles. So if we looked, like which one would be a disk, I think all of these have a hole in the middle somewhere. This one doesn't look like it does. So this would be made out with disks. You stacked up a whole bunch of coins together. That's what we're doing. Now, how do you find the volume of that disk? Well, take the volume of that circle. So how does that relate to us? Well, we're going to take some curve, maybe something like this, and then we're going to rotate that curve. And it would create something. Let's see how good my art skills are. Ooh, no. Can you guys imagine what's going to happen here? There we go. Maybe something like that. Oh, I missed it. I'm going to revolve it, and then create that three-dimensional object. Like so, by revolving something around that. Okay. All right, we can do this using the vertical x-axis or horizontal y-axis, and this would be our setup for our differential. There are some times where they'll give us a y-axis revolution one. Just take the same object and spin it around the y-axis. In the past, we maybe cut out some figures and add it to our pencil. Then you just rotate your pencil really quick, and you can see that three-dimensional figure being made. Maybe we'll do that. Maybe not. We'll see. All right. Let's find the volume of the solid that's revolved around the x-axis. Okay. So in this case, R, capital R, is always the height of the function. It's the distance from the x-axis to the curve. That's our radius, guys. That's extremely important to realize that. Well, we know the points on the graph are the heights, but it's also the radius of a circle that's going to be being revolved. It's going to be spinned. Okay? So this is our capital R. Our function is our capital R. Okay? Our interval is 0 to pi. So our antiderivative would be pi from 0 to pi, just because it's a trig function. And then we have square root sine x. Are we okay with this so far? Okay, the radius is the height of the function. Area, width, creates volume. Okay. Good news. Do a little bit of simplification, right? Square root of a square of a square root would simplify. So we have pi, antiderivative, 0 to pi, sine of x, dx. And here's the important thing, guys, is after you have your setup, after you have your setup, kind of ignore everything else and just take care of that antiderivative then. Okay. Sometimes you start thinking about, oh, can I do this? Can I do this? Because we're doing volumes. Well, this is the antiderivative that gives you the volume of that object. Just find the antiderivative now, ignore the rest of the problem for a minute. Okay? And just do everything legally, mathematically, please. Okay, what's the antiderivative of sine? What is it? Negative cosine. So pi times negative cosine x evaluated 0 to pi. All right, and then that's not too bad. Pi times negative cosine pi minus negative cosine 0. Mr. Bonley, why is this pi out in front? And we have pi up here. Well, okay, it's pi is part of the formula, and then pi is part of the boundaries. Don't confuse the two. Negative cosine pi. Cosine of pi is what? Negative 1. So opposite negative 1 would be positive 1. Cosine 0 is 1, and that's going to be plus 1. 1 plus 1 is 2, so 2 pi. What are the units, guys? Units cubed. So the volume of that object was 2 pi units cubed. Obviously, you guys can walk in all the way if you need to see stuff. Again, decimal approximations will be fine. Exact is actually better, obviously, when working on it. Okay? Questions on this? It's pretty easy, isn't it? See how easy it is. Revolving about a line that is not a coordinate axis. Now, this is where things get a little bit complicated, okay? Find the volume of the solid formed by revolving the region bound by the graphs of f of x equals 2 minus x squared and g of x equals 1 about the line y equals 1. So we're taking this function, this upside down quadratic, shifted up 2 units. Sketch that real quick. Then we have 1, 1. Then we have 2, and negative 4. About right there. That's good enough. Again, just a rough sketch is okay. So we're taking this guy, where it intersects with g of x equals 1. Okay, that's a horizontal line right here. And we're taking this area, and then we're revolving it. We're spinning it, right? So it's basically creating that egg shape that's lifted up off the x-axis, right? Okay, so if you revolve that, it would look like this, and we have a solid that could shade it really nicely, but we don't need to do that right now. Okay. Thing is, we got to create the boundaries. What would the boundaries be on this one? Yeah, negative 1 to 1. So we'd go from negative 1 to 1 where these lines intersect. So our differential will be negative 1 to 1, right? We have pi out in front. Now here's the problem with this question, or here's the problem with this problem. The radius. The radius is the distance from the axis of revolution to the curve, right? Before, over here, the x-axis was the axis of revolution, so it's just the height of the function, right? But the height of the function is this, that distance, right? However, we got to get rid of this distance. So how would we create this r, capital R, which is the radius from the axis of revolution to the function? We need this. Mathematically, how would we create that? How?
Take the area of the not shaded
Don't overcomplicate. You're finding the area. I just want the distance r, which would be a linear distance from. What do you guys say over there? Somebody say something over there? No? Somebody said 1. Where'd 1 come from? I heard 1 from somebody. You mean 2 minus x squared? Initial equations, 2 minus x squared, and then what? Is it equal? Okay, here's the deal, guys. This is going to give us every value here, right? The function will, right? I don't need those values. I need these values. Subtract their function, yeah. Which is 1. Minus 1. So that would be our capital R then. And think about this, guys. Didn't we just find area between curves yesterday? Top function minus bottom function. That's all it is. Top function minus bottom function. Okay. So there we go. We got 2 minus x squared. Obviously, we'd be using parentheses if there's more than just 1 right here. Squared and then dx. Okay, simplify first. What is that? 1 minus x squared? Squared. Now, if you had to find this by hand, can we do it the way it's written right now? No, we got to multiply this out, right? Let's multiply it out. I don't know what's happening there. So that'd be 1 minus, what, 2x squared plus x to the 4th. And then we can antiderive. Help me out with that. What's the antiderivative? And I think you meant to say 3 up here, right? I don't know. I didn't hear it. I'm getting old. Okay, and that's not too bad, right? Okay, so big idea, guys. We got to focus on this capital R. Okay, we got to focus on the radius, which is the distance from the axis of revolution to the function. Okay, if the axis of revolution is not the x-axis, you got to subtract out the axes. Okay, cool. Well, Mr. Bonding, I don't have a problem like this. I don't think, actually. Yeah, I don't have a problem like this. And are you okay if I don't finish this? We're good. And I think it's what? It's 16/15 pi, if I remember right. You can check your work. Well, Mr. Bonney, what if, I know I'm going to give you guys some of these, what if the axis of revolution is right here, let's say at, I don't know, y equals 3, but the function is right here. Now what? I need this distance, don't I? That is still capital R. Distance from axis of revolution to your function. Okay? How do we get this distance? And remember, the function, let's say f of x, will give you all of these heights, right? How do I get these heights? Well, if you had to find the area under this curve, between these two curves, what would you do? Top curve minus bottom curve, right? It's still the same idea. Top curve minus bottom curve. So it'd be 3 minus f of x. That would give you this little distance here. And you'd integrate from a to b, and then dx. And then put your pi out in front, and your radius is squared. Okay? So if your axis of revolution is above your function, it's still going to be top function minus bottom function. Must be axis of revolution minus the function they give you. The function is below, quantity squared. This is your R. Okay? Questions on that at all?